There is a world in our solar system where it rains liquid fuel, where rivers of methane carve valleys into frozen bedrock, and where seas the size of Earth's Great Lakes sit beneath a sky so thick with orange haze that no human eye has ever seen the ground from above. For 350 years after its discovery, this world hid everything behind the densest atmosphere of any moon ever found. Then we sent a spacecraft through the haze, and what we found was not what anyone expected. Beneath Titan's atmosphere is not a dead, frozen rock. It is a planet-like world with weather, coastlines, chemistry, and possibly warm pockets of liquid water buried beneath miles of alien ice. This is what Titan is really hiding. If you enjoy journeys that completely change how you see the worlds around us, I would genuinely appreciate it if you hit that like button and subscribe. It helps more than you know, and it means these deep dives keep coming. Now, settle in and get yourself comfortable. Let's begin. On the 25th of March, 1655, a Dutch mathematician pressed his eye against a telescope he had ground by hand and noticed something no human being had ever seen. A tiny point of light hovered near Saturn. It was faint, barely distinguishable from the scattered glow of the planet's rings, but it moved. Night after night, it traced a slow, steady arc around the giant world, and Christiaan Huygens realized he was watching a moon. He named it Saturni Luna, Saturn's moon. Just that. No grand title, no dramatic announcement, a simple acknowledgement that the sixth planet from the Sun was not alone. What Huygens could not have known, what no human being would understand for another 349 years, was that he had just discovered the most elaborately disguised world in the solar system. Every other major moon would eventually yield its secrets to better telescopes, sharper instruments, and closer spacecraft. Titan would not. Titan would resist every attempt to see its surface for nearly 3.5 centuries, and when we finally punched through the veil, what waited underneath would turn out to be stranger than anything the astronomers who spent those centuries staring at it had ever dared to imagine. For most of those 350 years, Titan existed as nothing more than a dot. A reliable, predictable dot that orbited Saturn once every 15 days, 22 hours, and roughly 41 minutes. But a dot nonetheless. Early telescopes could not resolve any detail. Later telescopes could not either. By the 19th century, astronomers had begun to suspect that something unusual surrounded Titan, because its disk appeared slightly fuzzy compared to other moons of similar size. But suspicion is not understanding. The fuzzy edge could have been an optical artifact, a trick of turbulent atmosphere above European observatories, a defect in glass. Nobody could prove that Titan had an atmosphere, and without proof, nobody could explain why it refused to show its face. The confirmation came in 1944, when Gerard Kuiper pointed the 82-inch reflector at McDonald Observatory toward Titan and detected methane absorption bands in its spectrum. Methane, a simple hydrocarbon gas that should not have been there. Moons were supposed to be dead objects, gravitationally too weak to hold onto any meaningful envelope of gas. Our own moon has essentially no atmosphere. The 4 Galilean moons of Jupiter were known to be airless or nearly so. Yet Titan was clearly wrapped in something substantial enough to contain measurable methane. Kuiper had proven the atmosphere existed, but the discovery deepened the mystery rather than solving it. If Titan had an atmosphere, how thick was it? What else was in it? And most importantly, what did the surface look like underneath? Nobody could answer these questions. Not with ground-based telescopes, not with the instruments available at the time. Methane absorbs and scatters visible light in ways that turn a planetary atmosphere into a one-way mirror. You can detect the gas spectroscopically from the outside, but you cannot see through it to whatever lies below. Titan's atmosphere was not transparent like the thin carbon dioxide shell around Mars. It was opaque. Utterly, stubbornly, maddeningly opaque, and it would stay that way for decades. The space age arrived, and with it came the first opportunity to get a closer look. In September of 1979, Pioneer 11 flew past Saturn and returned the first spacecraft images of the system. The pictures were crude by modern standards, but they confirmed what telescopes had hinted at. Titan appeared as a smooth, featureless orange sphere. No craters, no mountains, no surface markings of any kind. Just a uniform golden haze stretching from limb to limb, revealing absolutely nothing about what lay beneath. Then came Voyager 1. In November of 1980, the spacecraft made a close approach to Titan, passing within roughly 6,500 kilometers of its cloud tops. This was supposed to be the moment of revelation. Voyager carried cameras far superior to Pioneer's instruments. Mission planners had deliberately targeted Titan as a priority, routing Voyager 1's trajectory for the closest possible flyby. Even though the maneuver meant sacrificing the spacecraft's ability to visit Uranus and Neptune afterward, that is how badly scientists wanted to see beneath the haze. They traded 2 entire planets for a single, close look at one moon. The images came back and the disappointment was crushing. Titan showed nothing. The cameras recorded the same featureless orange ball that Pioneer had seen, only in higher resolution and with more exquisite clarity. The haze was so thick, so uniformly distributed, and so effective at scattering sunlight that Voyager's cameras could not detect a single surface feature through it. Not one. Scientists tried every image processing technique available. They enhanced contrast. They stacked frames. They filtered for specific wavelengths. Nothing worked. Titan simply would not reveal itself. But Voyager 1 did return critical data about the atmosphere itself. The spacecraft's instruments measured temperatures, pressures, and compositions that painted a picture far more complex and far more unsettling than anyone had predicted. Titan's atmosphere was not a thin methane shell clinging to a frozen rock. It was massive. The surface pressure measured approximately 1.5 times Earth's sea level atmospheric pressure. Think about that for a moment. You're standing on the surface of a moon roughly 40% the diameter of Earth, a world with only 1/7 of our planet's gravity, and the air above you is pressing down harder than the air presses down at sea level in New York or Tokyo. On Earth, our atmosphere stays put because our planet has enough gravity to hold nitrogen and oxygen molecules against the pull of space. Titan has far less gravity, yet it holds an atmosphere denser than ours. The explanation lies in temperature. Titan's surface sits at approximately -179 degrees Celsius, so cold that gas molecules move sluggishly and lack the energy to escape even weak gravity. The cold acts as a trap. Molecules that would easily float away from a warm moon become prisoners on a frozen one. Voyager also confirmed that the atmosphere was not primarily methane, as Kuiper's original detection might have implied. Methane made up only about 5% of the lower atmosphere. The dominant gas was nitrogen, accounting for roughly 95% of the atmospheric composition. This was startling. Nitrogen dominates Earth's atmosphere as well, making up about 78% of the air we breathe. Titan and Earth shared the same primary atmospheric gas. No other moon in the solar system had anything remotely comparable. Titan was not just unusual, it was unique among every known satellite orbiting every known planet. But the nitrogen and methane were only part of the story. What made Titan truly impenetrable was not the bulk gases themselves, but what happened when sunlight hit them. High in the atmosphere, ultraviolet radiation from the sun breaks apart methane molecules. The fragments, carbon and hydrogen atoms and radicals, do not simply recombine into methane. They react with each other and with nitrogen to form increasingly complex organic molecules. Ethane, ethylene, acetylene, hydrogen cyanide, benzene. These molecules polymerize further, linking together into long chains and clusters of carbon-rich compounds that scientists eventually called tholins, a term coined by Carl Sagan and Bishan Kare, from the Greek word for muddy. Tholins are not a single substance. They are a family of complex reddish-brown organic polymers that form through photochemistry in nitrogen-methane atmospheres. In laboratory experiments designed to simulate Titan's upper atmosphere, researchers have produced tholins by irradiating mixtures of nitrogen and methane with ultraviolet light or electrical discharges. The resulting material is a sticky tar-like residue that absorbs visible light with extraordinary efficiency. And on Titan, these tholins form continuously, day after day, century after century, accumulating in the upper atmosphere as an aerosol haze that blocks virtually all visible wavelengths from reaching the surface or escaping from it. The haze is not a single cloud layer. It is a vertically extended structure stretching from roughly 300 kilometers altitude down toward the surface, with distinct layers and detached haze regions that shift with Titan's seasons. The particles are minuscule individually, often only fractions of a micrometer in diameter, but their cumulative effect is devastating to optical observation. They scatter short wavelength light preferentially, which is why Titan appears orange rather than blue. The particles absorb and redirect photons so thoroughly that standing on Titan's surface would feel like standing in a thick, perpetual twilight. The sun would be invisible as a distinct disk. The sky would glow with a dim, diffuse amber illumination, bright enough to see by but too scattered to cast sharp shadows. This photochemical haze is what defeated Voyager's cameras. It is what defeated every ground-based telescope before and after Voyager. It is the reason Titan remained hidden for so long, while every other major moon in the solar system surrendered its secrets. Europa, discovered just 45 years before Titan, had its icy surface mapped in detail by the Voyager missions. Ganymede, the largest moon in the solar system, showed grooved terrain and ancient impact basins. Callisto displayed a battered, cratered face billions of years old. Even Io, shrouded in volcanic fumes, revealed its eruptions and sulfur plains. These moons wore their stories on their surfaces for any sufficiently capable instrument to read. Titan wore a mask, and the mask was not merely visual, it was conceptual. Because no one could see the surface, no one could constrain what the surface might be. This absence of data created a vacuum that speculation rushed to fill, and the speculation went in wildly different directions. Some scientists proposed that Titan's surface was covered in a global ocean of liquid hydrocarbons. The reasoning was straightforward. Methane in the atmosphere should slowly be destroyed by photochemistry, broken apart by ultraviolet light into fragments that form tholins and other complex molecules. If methane were not somehow replenished, it would vanish from the atmosphere within roughly 10 to 30 million years. Since Titan clearly still has methane, something must be supplying it. A vast surface reservoir of liquid methane and ethane seemed like the most natural source. This ocean hypothesis gained traction because the temperatures and pressures at Titan's surface fall squarely within the range where methane and ethane exist as liquids. On Earth, we think of methane as a gas, the primary component of natural gas that heats homes and powers stoves. But cool it down to minus 161 degrees Celsius, and methane condenses into a clear, colourless liquid. Titan is cold enough for this to happen naturally. Other scientists propose the opposite. Maybe the surface was solid, covered in a deep layer of frozen organic sludge accumulated over billions of years of photochemical production. The tholins raining out of the atmosphere would pile up centimetre by centimetre, millennium by millennium, burying the original icy surface under kilometres of organic sediment. This scenario predicted a surface that was dark, solid, and utterly unlike any terrain found elsewhere in the solar system. Still others suggested a compromise, that the surface might be partially liquid and partially solid, with hydrocarbon lakes or seas occupying low-lying areas while organic sediments blanketed the highlands. Some models predicted methane rain falling from the sky, carving channels through frozen terrain, feeding rivers that drained into lowland basins. These predictions sounded like science fiction in the 1980s and 90s. A moon with rain, rivers, and seas sounded absurd. Moons were supposed to be dead. Moons were supposed to be geologically inert spheres of rock or ice, pockmarked by craters and unchanged for billions of years. The idea that a moon could have an active meteorological cycle, with clouds and precipitation and surface liquids, violated every instinct astronomers had developed from studying the rest of the solar system. Yet the data allowed all of these possibilities. That was the maddening thing about Titan before Cassini. The haze prevented direct observation, and without direct observation, the models could say almost anything. Titan was a Rorschach test for planetary scientists. You saw in it whatever your theoretical framework suggested, and no one could prove you wrong. This uncertainty drove the European Space Agency and NASA to do something unprecedented. They decided to build a probe specifically designed to descend through Titan's atmosphere, survive the landing, and transmit data from the surface. No spacecraft had ever attempted anything like this at such a distance from the Sun. The target was a world roughly 1.5 billion kilometers away, hidden behind an atmosphere whose structure was only partially understood, with surface conditions that were largely unknown. The probe would need to carry instruments capable of measuring atmospheric composition during descent, photographing whatever emerged from the haze, and analyzing whatever the surface turned out to be, liquid, solid, or something in between. The probe was named Huygens, after the astronomer who had first spotted Titan's tiny point of light 3.5 centuries earlier. It was a flat, disc-shaped capsule roughly 2.7 meters in diameter, equipped with 6 instrument packages, a heat shield for atmospheric entry, and 3 successive parachutes to slow its descent through the thick atmosphere. Huygens carried cameras, a gas chromatograph mass spectrometer to identify chemical compounds, sensors to measure temperature, pressure, and wind speed, an instrument to analyze surface properties upon impact, and a radar altimeter to measure its height above the ground during the final phase of descent. Every instrument was chosen to answer a specific question about what lay beneath the haze. Every gram of payload mass was fought over during design reviews. The probe had to be light enough to fit aboard the Cassini orbiter, rugged enough to survive 7 years of interplanetary travel, and sophisticated enough to characterize an entirely unknown world in a descent lasting only a few hours. Cassini-Huygens launched on October 15, 1997, from Cape Canaveral aboard a Titan IV rocket. The spacecraft was enormous by interplanetary standards, approximately 5,700 kilograms, fully fueled, carrying 12 scientific instruments on the orbiter and 6 on the Huygens probe. The mission required 2 gravity assists from Venus, 1 from Earth and 1 from Jupiter to reach Saturn, a trajectory that took nearly 7 years to complete. Cassini entered orbit around Saturn on June 30th, 2004, becoming the first spacecraft to orbit the ringed planet. For 6 months, Cassini studied the Saturn system while carrying Huygens' piggyback. Engineers tested communication links. Scientists refined atmospheric models using data from Cassini's early Titan flybys. The orbiter carried a radar instrument that could penetrate the haze using microwave wavelengths, and during those initial passes, it began returning the first crude maps of Titan's surface. The radar images were low in resolution, fuzzy and ambiguous, but they hinted at something no one had expected. The surface was not uniform. It appeared to have distinct bright and dark regions, with textures that varied dramatically from one area to another. Some patches were smooth, others were rough. A few regions showed patterns that looked disturbingly like coastlines, but radar maps from orbit could only reveal so much. To truly understand what lay beneath the haze, something had to go down through it. On December 25th, 2004, Christmas Day, Cassini released the Huygens probe. There was no dramatic separation. The clamps holding Huygens to the orbiter's side released, and small springs pushed the probe gently away at about 30 centimeters per second. A walking pace. Huygens had no propulsion of its own. It drifted in silence for 20 days, coasting toward Titan on a trajectory that had been calculated years in advance, crossing the final stretch of space between orbiter and moon, with no ability to adjust its course. On January 14, 2005, Huygens hit Titan's upper atmosphere at approximately 6 kilometers per second. The heat shield absorbed the brutal deceleration, glowing white-hot as friction converted kinetic energy into thermal energy. Within minutes, the probe slowed enough for the first parachute to deploy, a small drogue chute that pulled away the heat shield and exposed the instruments to the atmosphere for the first time. Then the main parachute opened, 8.3 meters in diameter, and Huygens began its slow, swinging descent through the thickest part of the haze. For the first time in history, instruments were tasting the air of another world's atmosphere from the inside. The gas chromatograph confirmed nitrogen and methane in the expected proportions. Temperature sensors recorded conditions colder than anything found naturally on Earth's surface. The cameras began shooting frames, but for the first several minutes, they captured nothing but orange murk. Dense haze filled every direction. The probe was falling through a world made of fog. Then, at roughly 70 kilometers altitude, the haze began to thin. Faintly at first, then more clearly, shapes materialized below. Dark patches, light patches, lines that curved and branched. The cameras were seeing Titan's surface, or at least the rough outlines of it, for the first time. At 40 kilometers, details sharpened. At 20 kilometers, the images became unmistakable. Huygens was descending toward terrain that looked like a coastline. Bright, elevated regions with branching dark channels cutting through them, running downhill toward a flat, dark plain. The channels looked like river valleys seen from an airplane window. They branched, merged and widened as they descended toward lower elevations, exactly the way drainage networks behave on Earth when water flows downhill and carves its path through soil and rock. But on Titan, the liquid was not water. The rock was not rock. The rivers were carved by liquid methane flowing over bedrock, made of water ice, frozen so hard at minus 179 degrees Celsius that it behaves like granite. Everything was inverted from earthly experience. The roles of rock and liquid had been swapped. Ice was the stone, hydrocarbons were the fluid, and the landscape bore the unmistakable fingerprints of active erosion by flowing liquid. Huygens landed on January 14th, 2005, at a velocity of roughly 4.5 meters per second, a firm impact but well within the probe's structural tolerances. It struck what turned out to be a soft, slightly damp surface. The penetrometer, an instrument designed to measure how the surface responded to the impact, detected a thin crust that crunched slightly upon contact, overlying a softer layer below. The immediate suggestion was a surface of compacted organic particles with a damp hydrocarbon substrate, like wet sand on a beach after the tide retreats. The cameras captured the final frames from the surface itself. The images showed a flat, dark plain littered with rounded pebbles and cobbles of water ice. The pebbles were smooth, their edges worn down, their shapes eerily familiar to any geologist who had studied riverbeds on Earth. Rounded pebbles mean transport by flowing liquid. The tumbling action of liquid carrying stones downstream knocks off sharp edges and produces the smooth, ovoid shapes visible in the Huygens photographs. These were not random ice chunks scattered by an impact. These were river stones, transported and shaped by methane flowing across Titan's surface at some point in the past. The gas chromatograph detected a sudden spike in methane concentration at the moment of landing, consistent with liquid methane evaporating from the damp surface upon being disturbed by the probe's impact. Huygens had landed in what appeared to be a dry riverbed or floodplain, a region that had recently been wet with liquid methane and still retained enough moisture to release detectable vapor when the ground was disrupted. Huygens transmitted data for roughly 72 minutes after landing before its batteries died. In those 72 minutes, it returned 350 images and a wealth of atmospheric and surface measurements. It was the most distant landing ever achieved by a human-made object. It was also, arguably, the single most revealing 72 minutes in the history of planetary exploration, because what Huygens showed was not a dead moon. It was not a featureless wasteland. It was not a global ocean or a uniform sludge plain. It was a world with terrain shaped by flowing liquid, a world with a complex atmosphere driving a meteorological cycle, a world whose surface told the story of active geological processes operating under conditions found nowhere else. And Huygens was only the beginning. Cassini would continue orbiting Saturn for another 12 years, conducting over 120 close flybys of Titan, mapping its surface with radar, studying its atmosphere with infrared instruments, and peeling back layer after layer of concealment. What the orbiter found during those years would make the Huygens landing look like a prologue, because the probe had touched down in a relatively bland equatorial region. The truly astonishing features, the ones that would force scientists to rethink what a moon could be, were waiting at the poles. The haze that had hidden Titan for 3.5 centuries had not just been concealing terrain, it had been concealing a category of world that nobody believed could exist on a satellite. And the first real evidence of what that world contained was about to emerge from Cassini's radar, painting a picture so strange that some researchers initially refused to believe the data was real. Cassini's radar instrument did something that no camera in history could do. It ignored the haze entirely. Synthetic aperture radar operates at microwave wavelengths, frequencies so long that the tiny tholin particles in Titan's atmosphere are invisible to them. The microwaves pass through the haze the way radio signals pass through fog, unimpeded, undistorted, and reach the surface below. When they bounce back, they carry information about the terrain they struck. Rough surfaces scatter microwaves in all directions and appear bright. Smooth surfaces reflect them away from the spacecraft and appear dark. Liquid surfaces, being nearly perfectly flat, reflect almost all incoming energy away at an angle, returning virtually no signal to the orbiter. They appear as pitch-black voids in radar images. During Cassini's first dedicated radar pass of Titan's North Polar region in 2006, the instrument returned an image that made the science team go quiet. Vast stretches of terrain near the North Pole appeared as absolute black, not dark grey, not slightly dimmer than surrounding terrain. Black, signal-free. The kind of radar return that could only mean one thing: a surface so flat and so smooth that it could only be liquid. The features had irregular shapes. They were bounded by complex winding shorelines. Some were small, roughly circular, looking like water-filled volcanic craters on Earth. Others were enormous, with branching inlets, peninsulas, and channels connecting them to neighbouring dark patches. The science team was staring at lakes, not metaphorical lakes, not features that loosely resembled lakes if you squinted. Actual bodies of standing liquid sitting on the surface of a moon, 1.5 billion kilometres from the sun. Within months, as Cassini accumulated more radar swaths on successive flybys, the picture expanded dramatically. The northern polar region was not home to a few isolated ponds. It was a lake district. Dozens of dark features clustered between roughly 60 and 90 degrees north latitude, ranging in size from a few kilometres across to bodies so large they deserved a different word entirely. Scientists began calling the largest features seas, adopting the Latin word mare, in keeping with the tradition used for dark regions on Earth's moon. 3 seas dominated the northern landscape. The largest was Kraken Mare, an irregularly shaped body stretching roughly 1,170 kilometres in its longest dimension. For comparison, that is larger than the Caspian Sea measured in one direction and roughly equivalent in total area to the combined Great Lakes of North America. Kraken Mare is the single largest known body of stable liquid on any world other than Earth. To its east lay Ligeia Mare, roughly 500 kilometres across, and farther north sat Punga Mare, smaller but still substantial. Together, these 3 seas contained enough liquid methane and ethane to dwarf any lake system on Earth by sheer alienness, if not by total volume. The liquid filling these basins is not water. It is primarily methane, mixed with significant amounts of ethane and trace quantities of dissolved nitrogen and other hydrocarbons. At Titan's surface temperature of approximately -179 degrees Celsius, methane behaves the way water behaves at room temperature on Earth. It flows, it evaporates, it forms clouds, it rains, it pools in depressions and fills basins. The substance is different, but the behaviour is hauntingly familiar. Cassini confirmed that the seas were genuinely liquid through multiple independent methods. Radar reflections from their surfaces showed specular glints, mirror-like reflections that occur only when microwaves bounce off a perfectly smooth surface. Infrared observations caught the sun's reflection glinting off Jingpo Lacus in 2009, a flash of light bouncing off a liquid surface like sunlight, reflecting off a lake seen from an airplane. Subsequent radar altimetry measurements penetrated the surfaces of the smaller lakes and measured their depths. Ligeia Mare turned out to be roughly 160 meters deep in places. The radar signals passed through the liquid and bounced off the lake bed below, confirming that the fluid was remarkably transparent to microwaves and that solid terrain existed beneath it. The bathymetry of these seas revealed something else. The lake beds were not uniform. They had contours. Shallow edges sloped into deeper central basins. Channels connected some lakes to others, suggesting that liquid flowed between them seasonally or episodically. A few lakes appeared partially empty, with bathtub ring-like deposits around their margins indicating that liquid levels had dropped over time, leaving behind residues of heavier hydrocarbons. Titan's seas were not static features. They were dynamic. They rose and fell. They filled and drained. They responded to forces that operated on timescales scientists were only beginning to understand. The distribution of lakes and seas revealed a striking asymmetry. Nearly all of Titan's large liquid bodies clustered in the northern hemisphere. The southern hemisphere, by contrast, was almost dry. It contained only a single large lake, Ontario Lacus, a kidney-shaped body near the South Pole, roughly 235 kilometers long. This imbalance puzzled researchers until they considered Titan's orbital mechanics. Saturn orbits the Sun on a slightly elliptical path, and Titan's seasons are influenced by this eccentricity. Northern summers are long and cool, southern summers are short and intense. This means the South Pole receives more concentrated solar heating during its brief summer, potentially driving more evaporation and leaving fewer stable liquid bodies. The North Pole, with its longer, milder summer, retains its lakes more effectively. The hemispheric asymmetry is a direct consequence of orbital dynamics governing a weather cycle operating across a moon 1.5 billion kilometers from the Sun. That weather cycle represents one of the most profound discoveries in planetary science. Before Cassini, only Earth was known to have an active hydrological cycle, a system in which a substance evaporates from the surface, rises into the atmosphere, condenses into clouds, falls as precipitation, flows across the landscape as rivers, and collects in standing bodies of liquid. Every introductory geology textbook describes this cycle as a defining feature of our planet. It drives erosion. It shapes terrain. It redistributes chemicals across continents. It sustains every terrestrial ecosystem. Finding the same fundamental process operating on Titan, with methane substituting for water, was not a minor footnote. It was a conceptual earthquake. Cassini observed Titan's methane weather cycle in action. The spacecraft's cameras and infrared spectrometer detected clouds forming in Titan's lower atmosphere, particularly near the poles and occasionally at mid-latitudes. The clouds were not permanent fixtures. They appeared, evolved, and dissipated over periods of hours to days, exactly as convective clouds do on Earth. Some cloud systems were enormous, stretching hundreds of kilometers across, and their formation correlated with seasonal changes as Titan progressed through its roughly 29.5-year orbit around the Sun. In 2009, Cassini's instruments captured direct evidence of rainfall. A large cloud system appeared over Titan's equatorial region, and subsequent images showed darkening of the surface below, consistent with liquid methane, wetting the ground and temporarily changing its reflective properties. The wet area covered roughly 500,000 square kilometers and faded over weeks as the methane either soaked into the ground or evaporated. Scientists were watching a rainstorm on another world, observing the aftermath in real time across interplanetary distances. The rainfall does not behave like a gentle Earth drizzle. Modeling based on Cassini data and atmospheric physics suggests that Titan's methane rainstorms are infrequent but intense. The thick atmosphere and low gravity allow raindrops to grow very large, possibly reaching a centimeter or more in diameter, falling slowly through the dense air at roughly 1.5 meters per second. A methane rainstorm on Titan would look like enormous slow-motion droplets drifting down through orange twilight, each one a transparent bead of liquid hydrocarbon, catching the faint glow of a sun 9.5 times farther away than it appears from Earth. The rainfall events may be separated by years or even decades in some regions, but when they come heavily, releasing torrents that carve the landscape with concentrated force. Try to picture what a methane flash flood looks like on Titan. The sky, already dim, darkens further as cloud banks roll across the haze layer. For the first time in perhaps a decade, liquid begins to fall. The drops are huge by earthly standards, fat transparent globes that descend through the thick air with an almost lazy quality, drifting rather than plummeting. They strike the ground and burst across terrain that has been dry for years, wetting the dark organic crust, pooling in shallow depressions, trickling into hairline fractures in the water ice bedrock. Within hours, the trickles become rivulets. The rivulets find each other and merge into streams. The streams gather force as they flow downhill through valleys carved by identical storms in decades and centuries past, deepening channels that already exist, sometimes cutting new ones. The liquid is colourless, lighter than water, and startlingly fluid, because liquid methane is roughly 5 times less viscous than water, running thinner and faster than any terrestrial river would under comparable conditions. And the sheer volume makes the effect devastating. By the time the runoff reaches the lowlands, it is a torrent, carrying pebbles of water ice and flecks of dark organic sediment in suspension, depositing them in fans and deltas where the current slows. Then, over weeks, the flow diminishes. The river channels dry, the landscape returns to its patient, arid stillness, and it waits for the next storm, which might not come for another 10 or 20 years. The evidence of that carving is everywhere Cassini looked. Radar mapping revealed extensive networks of channels cutting through Titan's terrain, branching and merging in patterns that geomorphologists recognized instantly as fluvial networks, landscapes shaped by flowing liquid. Some channels were narrow and deeply incised, suggesting persistent or repeated flow. Others were broad and braided, resembling riverbeds in arid regions on Earth where seasonal floods spread across wide, shallow paths before drying up. A few channel systems terminated at the edges of the polar seas, draining directly into the liquid bodies like terrestrial rivers emptying into oceans. The most spectacular channel system discovered was Vid Flumina, a network of steep, narrow canyons in Titan's North Polar region. Radar data revealed that these canyons were flooded with liquid, their floors submerged beneath methane that appeared to be flowing toward Ligeia Mare. The canyon walls rose roughly 240 meters above the liquid surface. On Earth, a comparable feature would be a slot canyon filled with river water, its walls towering hundreds of meters overhead while a current runs through its depths. Vid Flumina demonstrated that Titan's liquid methane does not just sit passively in lakes. It flows through carved terrain, shaping and deepening channels over geological time. But rivers and seas were not the only surface features hiding beneath the haze. Cassini's radar revealed that Titan's equatorial regions, far from the polar lake districts, were dominated by an entirely different landform. Vast fields of linear dunes stretched across the low latitudes, running roughly east to west in parallel lines that extended for hundreds of kilometers. These dunes are made not of silicate sand as on Earth or Mars, but of organic particles. The tholin haze produced in the upper atmosphere eventually settles to the surface. Over time, these particles accumulate, are reworked by winds, and pile into dune ridges that bear an uncanny resemblance to the linear dunes found in the Namib Desert of southern Africa. The dune fields cover approximately 12.5% of Titan's total surface area, concentrated in a broad band around the equator. Individual dunes reach heights of roughly 100 meters and widths of 1 to 2 kilometers, separated by interdune corridors of exposed water ice bedrock or compacted organic material. The dunes tell a story about Titan's wind patterns. Their orientation indicates that near-surface winds at equatorial latitudes blow predominantly from west to east, consistent with atmospheric circulation models that predict eastward flow near the surface due to Titan's slow rotation and thick atmosphere. The organic material composing the dunes is itself remarkable. These are particles manufactured in the atmosphere through photochemistry, rained out onto the surface, and then sculpted into landforms by wind. The entire process is a chemical assembly line that begins with simple methane and nitrogen in the upper atmosphere and ends with complex organic sediments piled into 100-meter-high ridges on the ground. No other world in the solar system has anything comparable, a surface shaped by the deposition and reworking of photochemically produced organic material. Cassini also identified features that may represent cryovolcanism, volcanic-like processes driven not by silicate magma, but by the eruption of volatile materials such as water, ammonia, or methane from Titan's interior. Several regions showed flow-like features in radar images, areas where material appeared to have spread across the surface from central vents or fissures. The most debated candidate was a feature called Sotropatera, a deep pit roughly 1.5 kilometers deep adjacent to what appeared to be a volcanic dome and associated flow structures. If Sotropatera is genuinely cryovolcanic, it implies that Titan's interior is warm enough to mobilize subsurface volatiles and drive them to the surface, a finding with profound implications for what might exist deeper inside the Moon. The question of Titan's surface age added another layer of strangeness. Impact craters, the scars left by asteroid and comet collisions, serve as a clock for planetary surfaces throughout the solar system. Old surfaces accumulate craters over billions of years. Young surfaces have fewer craters because geological processes erase or bury them. Mercury, the Moon, and Callisto are ancient cratered worlds. Their surfaces record billions of years of bombardment. Titan, by contrast, has remarkably few confirmed impact craters. Cassini identified only a handful of probable impact structures across the entire Moon, despite Titan being large enough and exposed enough to have accumulated many more over the age of the solar system. The scarcity of craters means that Titan's surface is geologically young. Something is actively erasing or burying impact scars. The candidates are exactly the processes Cassini observed: erosion by methane rainfall and river flow, burial by organic sediment accumulation, and possibly cryovolcanic resurfacing. Titan is not a frozen museum of ancient impacts. It is a world whose surface is continuously reworked by ongoing geological and meteorological activity. Its face is young because its face is alive. This realization carried an implication that was easy to overlook amid the excitement of individual discoveries. Titan was not just a moon with a thick atmosphere and some interesting surface features. Titan was operating a planetary-scale chemical cycle that had no equivalent anywhere else in the explored solar system. Methane evaporates from the seas. It rises into the atmosphere. Ultraviolet light breaks it apart. The fragments recombine into complex organic molecules. Those molecules descend as haze particles and accumulate on the surface. Rainfall washes them into rivers. Rivers carry them into lakes and seas. Some fraction dissolves into the liquid methane. Some fraction settles to the bottom. Some fraction gets reworked by winds into dune fields. The entire surface participates in a continuous exchange of material between atmosphere, liquid, and solid, driven by energy from the sun, and sustained by the cycling of methane through multiple phases. This cycle has consequences that extend far beyond surface geology. The chemistry happening in Titan's atmosphere and on its surface is a natural experiment in prebiotic organic synthesis, the kind of chemistry that may have preceded the origin of life on Earth billions of years ago. When sunlight breaks apart methane and nitrogen in Titan's upper atmosphere, the resulting reactions produce exactly the kinds of molecules that astrobiologists consider critical precursors to biology. Hydrogen cyanide, which Cassini detected in Titan's atmosphere, is a key building block in the synthesis of amino acids and nucleobases, the molecular components of proteins and genetic material. The tholins settling onto Titan's surface contain a complex mixture of organic compounds whose full inventory has never been catalogued because no instrument has yet analysed them in detail. In October of 2025, a study published in the Proceedings of the National Academy of Sciences by researchers at Chalmers University of Technology and NASA revealed something that challenged a fundamental rule of chemistry. The team demonstrated through computational modelling that on Titan, hydrogen cyanide can form stable molecular mixtures with methane and ethane at the extremely low temperatures found on the surface. On Earth, Hydrogen cyanide is a polar molecule, and methane is non-polar. According to basic chemical principles, polar and non-polar substances do not readily mix, the same reason oil and water separate. But at Titan's surface temperatures, this rule breaks down. The molecules form co-crystals, stable hybrid structures where polar and non-polar species interlock in arrangements that would be impossible under warmer conditions. This discovery means that Titan's surface chemistry is not merely exotic, it operates under rules that differ from what chemists would predict based on terrestrial experience. The frozen landscape is a laboratory where molecular interactions follow pathways that have no counterpart on Earth. The implications deepened further in July of 2025 when NASA researchers published a study in the International Journal of Astrobiology describing a mechanism by which cell-like structures could form naturally in Titan's hydrocarbon lakes. The structures in question are vesicles, hollow spheres made of double-layered membranes of amphiphilic molecules, compounds that have one end attracted to methane and another end repelled by it. On Earth, amphiphilic molecules called lipids form the membranes of every living cell. They spontaneously assemble into vesicles in water, creating the compartments that separate a cell's interior chemistry from the outside environment. This compartmentalization is considered one of the essential steps toward the origin of life. To understand why vesicles matter, you need to understand what makes life different from ordinary chemistry. Chemical reactions happen everywhere. They happen in stars, in interstellar clouds, in volcanic vents, in the atmospheres of gas giants. But those reactions are diffuse. Their products scatter into the surrounding environment and dissipate. Life requires the opposite: concentration. It requires that certain molecules be kept together in a confined space where they can interact repeatedly, building complexity through sustained contact rather than losing it through dispersal. On Earth, the cell membrane provides that confinement. It creates an inside and an outside. It allows the chemistry within to become more complex than the chemistry without. Without compartmentalization, the molecular building blocks of biology would simply drift apart and never achieve the concentration necessary for self-sustaining reactions. Every origin of life researcher recognizes that the formation of compartments, however primitive, represents one of the most critical and least understood transitions from chemistry to biology. The NASA study proposed that a similar process could occur on Titan, but driven by methane rain rather than liquid water. When methane raindrops strike the surface of a hydrocarbon lake, they splash upward, creating a mist of tiny droplets. These droplets can become coated in thin films of amphiphilic organic molecules produced by atmospheric photochemistry and deposited on the lake's surface. When the coated droplets fall back and re-enter the lake, they acquire a second layer of amphiphiles, forming a double-layered vesicle that encapsulates a small pocket of methane. Over time, these vesicles would accumulate in the lakes, interact, and undergo a rudimentary form of selection, with more stable vesicle compositions persisting while unstable ones dissolved. The researchers described this as a potential pathway toward protocells, the simplest possible precursors to living cells. No one is claiming that Titan's lakes contain life. That is a critical distinction. What the study demonstrated is that the chemical and physical conditions on Titan's surface are capable of producing structures that represent an increase in molecular order and complexity, conditions that are considered necessary prerequisites for the origin of life. Whether those conditions are sufficient for life to actually emerge remains entirely unknown. But the fact that Titan's environment can independently generate cell-like compartments through purely physical and chemical processes is a finding with no parallel on any other world we have explored. What makes this finding so striking is the solvent. On Earth, vesicles form in water. Every model of terrestrial abiogenesis relies on water as the medium in which lipids self-assemble into membranes. If vesicles can also form in liquid methane, using different amphiphilic molecules under radically different temperature and pressure conditions, it suggests that compartmentalization is not a quirk of water chemistry, but a more general physical phenomenon that can occur in multiple liquid media. This broadens the theoretical landscape for the origin of life enormously. It means that the first step toward biology, the creation of a boundary between self and environment, might not require the specific conditions of early Earth. It might require only a liquid, a source of organic molecules, and an energy input, conditions that Titan provides through its methane weather cycle alone. Cassini also studied Titan's coastlines and found evidence that the seas are not entirely calm. Research published in 2024 used computer simulations to show that the shorelines of Titan's methane seas have likely been shaped by waves. The coastal morphology visible in radar images, the scalloped edges, the embayments, the patterns of erosion along exposed headlands, all matched what wave-driven erosion would produce. Titan's seas are not stagnant pools. They are bodies of liquid methane stirred by winds, lapping against frozen organic shorelines, slowly reshaping the geography of a world no human eye has ever seen directly. The cumulative picture that emerged from Cassini's 13 years at Saturn was not what anyone had predicted before the mission launched. No pre-Cassini model correctly forecast the full range of what Titan's surface contained. The global hydrocarbon ocean hypothesis was wrong. Titan does not have a single world-spanning sea. The solid organic sludge hypothesis was also wrong. Titan's surface is varied, with distinct terrains occupying different latitude bands. The compromise hypothesis of some lakes and some dry terrain was closest to reality, but even that prediction drastically underestimated the complexity. What Titan actually has is a world-spanning chemical system in which atmosphere, surface, and liquid reservoirs interact through cycles of evaporation, photochemistry, precipitation, erosion, and deposition. It has weather, it has seasons, it has coastlines shaped by waves, it has river valleys carved by flowing liquid, it has dune fields sculpted by wind, it has volcanic-like features that may connect the surface to a warm interior, and it has chemistry capable of producing molecular structures that echo the earliest steps toward biology, all operating at temperatures where water is frozen harder than steel, and methane takes the role that water plays on Earth. The first hidden layer beneath Titan's atmosphere was not the dead, frozen wasteland that decades of frustrated observation might have suggested. It was not empty. It was not simple. It was an active, complex, and chemically creative world unlike anything else orbiting any planet in our solar system. Huygens had revealed the first glimpse during its 72 minutes on the surface. Cassini spent 13 years filling in the rest, and every new radar pass, every infrared image, every spectroscopic measurement added another detail to a portrait that grew stranger with each addition. But the surface, as extraordinary as it turned out to be, was not the deepest layer of Titan's concealment. Beneath the rivers and the dunes and the methane seas, beneath the frozen organic crust and the water-ice bedrock, Titan was hiding something else. The data Cassini collected about how the moon flexed and shifted under Saturn's gravitational pull told a story about the interior that was, in some ways, even more shocking than what the surface had revealed. The next hidden layer lay below the ice, and as a landmark study published in December of 2025 would demonstrate what scientists thought they understood about that interior was about to be upended entirely. Every time Cassini flew past Titan, the moon tugged on the spacecraft. The pull was slight, a whisper of gravitational force acting across thousands of kilometers of empty space, but the Deep Space Network could measure it. Radio signals traveling between Cassini and Earth shifted in frequency as the spacecraft accelerated or decelerated under Titan's gravitational influence. These Doppler shifts, changes of mere fractions of a hertz in a signal oscillating billions of times per second, encoded information about how mass was distributed inside the moon. Heavier concentrations of material pulled the spacecraft harder, lighter regions pulled less. By tracking these infinitesimal frequency changes across 127 close flybys over 13 years, scientists built a three-dimensional map of Titan's internal gravity field with a precision that would have been unimaginable a generation earlier. What the gravity data revealed was the first indication that Titan's secrets did not stop at the surface. The moon's overall density, calculated from its mass and volume, came out to approximately 1.88 grams per cubic centimetre. This is significantly less dense than rock, which typically measures between 2.5 and 3 grams per cubic centimetre, but denser than pure water ice, which sits around 0.92. The number told scientists that Titan was made of a mixture of rock and ice in roughly equal proportions by mass. A rocky core sat at the centre, surrounded by layers of ice extending outward to the surface. This much was expected. Most large moons in the outer solar system share a similar rock and ice composition, but the gravity data contained a second signal that was far more provocative. As Cassini tracked Titan's gravitational field across multiple flybys, scientists noticed that the field was not static. It varied slightly depending on where Titan sat in its 16-day orbit around Saturn. When Titan was closest to Saturn, at the point in its slightly elliptical orbit called periapsis, the moon's shape was measurably different from when it was farthest away at apoapsis. Saturn's immense gravitational pull was physically deforming Titan, squeezing it along one axis and stretching it along another. This phenomenon is called tidal flexing, and it happens to every moon orbiting a massive planet. Earth's moon raises tides in our oceans through the same mechanism, but on Titan, the degree of deformation was extraordinary. To appreciate what tidal flexing means at Titan's scale, consider what is actually happening. Saturn is a gas giant 95 times more massive than Earth. It sits at the center of a gravitational well so deep that its influence physically reshapes solid bodies orbiting hundreds of thousands of kilometers away. As Titan moves through its elliptical orbit, the intensity of Saturn's pull fluctuates. At closest approach, Saturn's gravity is measurably stronger on the near side of Titan than on the far side, creating a differential force that stretches the moon into a slightly elongated shape. At maximum distance, the differential weakens and the moon relaxes back towards spherical. This cycle repeats every 16 days, and the amount of flexing depends entirely on what Titan is made of. A moon made of rigid, cold, solid ice throughout would barely respond. The stretching would be imperceptible. A moon with liquid inside would flex dramatically, its solid shell riding on a yielding interior the way a boat hull rides on water. The measurement that changed everything was a quantity called the tidal love number, designated K2. This parameter describes how much a body deforms in response to tidal forces. A perfectly rigid body, one made entirely of solid rock or ice frozen to absolute rigidity, would have a very low love number. It would barely flex at all. A body with a liquid interior would have a much higher love number because liquid allows the outer shell to deform more freely. Think of the difference between squeezing a billiard ball and squeezing a water balloon. The billiard ball resists. The water balloon yields. When Cassini scientists first analysed the tidal love number data in 2012, the result was striking. Titan's love number came out to approximately 0.6, far higher than what a completely solid ice and rock body would produce. The number was consistent with a model in which a solid ice crust floated atop a global layer of liquid. The implication seemed clear. Titan had a subsurface ocean. Beneath the frozen surface, beneath the methane rivers and organic dunes and hydrocarbon seas, there existed an entirely separate body of liquid. This one made not of methane but of water, possibly mixed with ammonia or other dissolved compounds that would lower its freezing point enough to remain liquid at Titan's internal temperatures. The announcement landed like a thunderclap in the planetary science community. A subsurface ocean on Titan would place it alongside Europa and Enceladus in the exclusive category of ocean worlds, bodies in the outer solar system that harbour liquid water beneath icy shells. Ocean worlds are considered prime targets in the search for extraterrestrial life because liquid water is the one substance that every known form of terrestrial biology requires. Finding water oceans hidden inside frozen moons suggested that habitable environments might be far more common in the universe than anyone had assumed during the decades when Earth appeared to be the only world with significant liquid water. For years, the subsurface ocean interpretation stood as the leading model of Titan's interior. Textbooks incorporated it. Mission proposals cited it. Popular science articles described Titan as a double ocean world, one with hydrocarbon seas on the surface and a water ocean below the ice. The picture was elegant and scientifically compelling. It placed Titan at the intersection of two extraordinary phenomena: an active methane cycle on the surface and a hidden water reservoir underneath, with an ice shell separating two fundamentally different liquid environments. Then, in December of 2025, a study published in the journal Nature dismantled this picture. The research was led by Flavio Petrica, a postdoctoral researcher at NASA's Jet Propulsion Laboratory, along with colleagues including Baptiste Journeau at the University of Washington. The team went back to the original Cassini Doppler data, the same radio frequency measurements that had produced the 2012 tidal love number, and applied a novel processing technique that reduced the noise in the signal. The original analysis had extracted the dominant tidal signal cleanly enough, but smaller features in the data had been buried beneath measurement uncertainty. Petrica's team found a way to suppress that noise, and when they did, a new signal emerged from the clean data. It was subtle but unambiguous, a signature of strong energy dissipation deep inside Titan. Energy dissipation in this context means friction. When a body flexes under tidal forces, internal friction converts some of the mechanical energy of deformation into heat. The amount and location of that dissipation depends on what the interior is made of. A global liquid ocean would dissipate very little energy because liquid flows freely with minimal friction. A solid ice interior would dissipate some energy, but the pattern would differ from what the team observed. What matched the data best was something in between: layers of partially melted ice, a slush, where ice crystals suspended in liquid generated friction as they rubbed against one another during each tidal cycle. The distinction between an ocean and a slush might sound minor, but it changes the fundamental picture of Titan's interior. An ocean is a coherent body of liquid with relatively uniform properties across its extent. Currents circulate through it. Heat distributes relatively evenly. Chemistry operates in a connected medium where dissolved substances can travel from one region to another. A slush is something profoundly different. It is a heterogeneous mixture of solid and liquid phases, a frozen matrix with liquid trapped in pores and channels between ice crystals. The properties vary from point to point depending on the local ratio of ice to water, the temperature, the pressure, and the composition of dissolved substances. A slush does not circulate the way an ocean does. It creeps, it oozes, it responds to forces on geological timescales rather than hydrodynamic ones. The interior that Petrica's team described was not a hidden sea waiting to be explored by a future submarine. It was a frozen labyrinth with warm liquid seeping through its interstices, a structure more analogous to groundwater moving through porous rock than to an ocean filling a basin. The implications were immediate and profound. If Titan's interior was slushy rather than liquid, the high love number, measured by the original analysis, could be explained without requiring a global ocean. The slush would be viscous enough to allow significant tidal deformation, explaining why Titan flexes so much, but it would dissipate energy far more strongly than a liquid ocean would, which is exactly what the new data showed. The team's model suggested that descending through Titan's ice shell would not lead to a sudden transition from solid ice to open liquid water. Instead, it would lead to gradually increasing proportions of liquid mixed with ice, layers of slush becoming progressively wetter and warmer with depth, until isolated pockets of liquid water formed near the rocky core. The pockets of liquid water in this model are not minor features. The study estimated that they could reach temperatures as warm as 20 degrees Celsius, roughly room temperature by human standards. This warmth is generated by tidal dissipation itself. The friction produced as Saturn's gravity kneads Titan's slushy interior creates heat, and that heat accumulates near the bottom of the ice shell where the slush is thickest and the dissipation is strongest. The warm water pockets would be in contact with Titan's rocky core, which means they could interact with rock minerals, potentially dissolving salts and other compounds that could serve as nutrients for hypothetical biological processes. The study also proposed that these water pockets are not stationary. Heated by tidal energy, the pockets slowly migrate upward through the slushy layers, rising toward the colder ice shell above. As they rise, they encounter organic molecules being supplied from two directions. From below, material leaches from the rocky core through hydrothermal interactions. From above, organic compounds produced in the atmosphere and deposited on the surface percolate downward through fractures and pores in the ice. The rising water pockets become enriched in organic chemistry as they travel, creating transient environments where water, warmth, rock-derived minerals, and organic molecules coexist. Picture the journey of a single water pocket through Titan's interior. It begins near the base of the ice shell, where tidal friction has melted enough ice to form a lens of warm liquid water a few meters or perhaps a few hundred meters across. The water is not pure. It contains ammonia dissolved from the surrounding ice, salts leached from the rocky core below, and traces of organic molecules that have trickled down through billions of years of slow percolation from the surface. The pocket is warm, perhaps 15 or 20 degrees Celsius, heated by the relentless kneading of Saturn's gravity. Buoyancy drives it upward. Warm water is less dense than the surrounding cold ice slush matrix, so the pocket rises, slowly, perhaps centimeters per year, perhaps less. As it ascends, it encounters colder temperatures. Its edges begin to refreeze. Some of the dissolved compounds precipitate out. The pocket shrinks. Eventually, hundreds of thousands or millions of years after it formed, the pocket freezes entirely, depositing its chemical cargo into the surrounding ice. But by then, new pockets are forming below, beginning their own slow ascent. The interior becomes a conveyor belt, a sluggish but persistent cycle of warm water rising and freezing, each pocket carrying dissolved substances upward through the ice shell, each one a temporary microenvironment that exists for a geological instant before being reclaimed by the cold. This is not the global ocean that the original Cassini analysis suggested. It is something stranger. Rather than a single vast sea beneath the ice, Titan may contain a distributed network of warm, nutrient-rich water pockets embedded in a matrix of semi-frozen slush, each pocket a temporary microenvironment cycling upward through the interior before eventually freezing as it reaches colder layers near the surface. The comparison that researchers offered was not to the open oceans of Europa or Enceladus, but to Arctic sea ice or terrestrial aquifers, systems where liquid water exists in confined, interconnected pockets within a predominantly frozen matrix. Baptiste Journeau, a co-author on the study, explained the distinction in terms that captured both its scientific significance and its implications for habitability. He noted that instead of an open ocean like Earth's, Titan's interior probably resembles something more like pockets and channels of water within ice, environments that are smaller, more isolated, but potentially more chemically diverse than a single homogeneous ocean would be. The variety of conditions across multiple water pockets, each at slightly different temperatures, pressures, and chemical compositions, could create a wider range of potential niches for hypothetical biology than a single uniform ocean. The December 2025 study did not prove that Titan lacks a subsurface ocean. It demonstrated that the Cassini data, when analysed with improved techniques, are better explained by a slushy interior with water pockets than by a global liquid layer. The distinction matters because the original ocean interpretation was not wrong given the data available at the time. It was the most straightforward explanation for the measured love number. The new analysis revealed additional information that the original processing had missed, and that additional information pointed toward a more complex interior structure. Future missions will be needed to determine which model is closer to reality. But as of the most recent analysis, the scientific consensus has shifted. Titan probably does not have a vast, continuous water ocean beneath its ice. It probably has something more complicated and, in some ways, more intriguing. The question of life in Titan's interior shifted accordingly. In April of 2025, a study published in the Planetary Science Journal by an international team co-led by Antonin Affolter at the University of Arizona examined what kind of life might theoretically survive in Titan's subsurface water. The team used bioenergetic modeling, a method that calculates how much energy is available to sustain metabolic processes, to estimate the potential biomass Titan's interior could support. They focused on fermentation, one of the simplest and most ancient metabolic strategies known on Earth. A process that requires only organic molecules and liquid water, with no need for oxygen or other oxidants. The choice of fermentation was deliberate. On Earth, fermentation is thought to have evolved very early in the history of life, possibly within the first few 100 million years after biology emerged. It is a metabolic strategy so basic that it requires no complex enzymatic machinery beyond what the simplest microorganisms possess. Fermenting organisms consume organic molecules like sugars or amino acids and extract energy by partially breaking them down, producing simpler waste products in the process. The energy yield is low compared to respiration, which uses oxygen, but fermentation works in environments where oxygen is absent, which describes nearly every subsurface environment on every icy moon in the solar system. If life exists in Titan's water pockets, fermentation is arguably the most plausible metabolic strategy it could employ, because it demands the least from its environment. It needs only organic molecules and liquid water, nothing else. The results were sobering in their modesty. The study concluded that Titan could theoretically support simple, microbial life through fermentation of organic molecules like glycine, but the total biomass would be minuscule. The supply of suitable organic material reaching the subsurface water is limited, even though Titan's surface is rich in complex organics. Most of the organic inventory remains locked in forms that are not readily usable as biological fuel. The total sustainable biomass across all of Titan's subsurface might amount to only a few kilograms, not a few kilograms per cubic meter, a few kilograms total across the entire moon. This finding does not rule out life on Titan. A few kilograms of microbial life is not zero, and the estimate depends on assumptions about which organic molecules reach the water pockets and how efficiently hypothetical organisms could metabolize them. If the actual chemistry is more favorable than the conservative assumptions in the model, the biomass could be larger. If less favorable, it could be smaller or non-existent. But the study established an important principle. Titan's organic richness on the surface does not automatically translate into biological richness underground. The surface and the subsurface are separated by kilometers of ice, and the pathways connecting them are narrow, slow, and inefficient. The interior story became even more complex in February of 2026, when a study led by SETI Institute scientist Matija Cuk proposed that Titan itself may have formed through the collision and merger of two older moons in the Saturnian system. The research used computer simulations to investigate the stability of Saturn's moon system over geological time, and found that a plausible evolutionary pathway involved a now destroyed moon interacting gravitationally with Titan, eventually colliding with it. The merger would explain several puzzling features of Titan, including its unusually few surface craters, its current orbital characteristics, and its relationship to Hyperion, Saturn's smallest major moon, whose orbit is locked in resonance with Titan's. If Titan formed through a giant collision, its internal structure would have been profoundly affected. The energy released by the merger of two moon-sized bodies would have been enormous, potentially melting large portions of the interior and resetting the geological clock. The relatively young surface age, inferred from the crater count, could be partly a consequence of this cataclysmic origin rather than solely the result of ongoing erosion and resurfacing. The internal layering, the distribution of rock and ice, and the thermal profile of the interior could all bear the imprint of a violent birth that occurred perhaps 500 million years ago, far more recently than the 4.5 billion year age of the solar system itself. This formation hypothesis remains a candidate explanation rather than a confirmed finding. The simulations showed that the collision scenario was plausible and could reproduce several observed features of the Saturnian system, but direct evidence would require detailed measurements of Titan's internal structure that no existing mission can provide. NASA's Dragonfly mission, currently under construction and scheduled to arrive at Titan in 2034, will carry geophysical instruments capable of probing the moon's interior, but whether its measurements will be sufficient to distinguish between formation scenarios remains to be seen. The layered picture of Titan's interior that has emerged from the past 2 decades of research represents a world of nested concealment. The atmosphere hides the surface. The surface, with its rivers and dunes and organic sediments, hides the ice shell below. The ice shell hides the slushy layers within it, and the slush hides pockets of warm liquid water that may represent the most habitable environments on the entire moon. Each layer of revelation has led to a deeper layer of mystery, and each deeper layer has turned out to be more complex than the one above it. The contrast with other ocean worlds in the solar system is instructive. Europa, Jupiter's ice-covered moon, is thought to have a relatively straightforward interior structure, a thin ice shell overlying a deep, global, salty ocean in direct contact with a rocky seafloor. The simplicity of this picture is part of what makes Europa such an attractive target for astrobiology. If you can get through the ice, you reach water. If the water touches rock, hydrothermal chemistry can supply energy and nutrients. The pathway from surface to potentially habitable ocean is conceptually clean. Enceladus, Saturn's small but spectacular moon, makes the case even more directly. Its subsurface ocean actively vents to space through cracks in the south polar ice, creating geysers that spray water vapor and ice particles into orbit around Saturn. Cassini flew through these plumes and detected water, salts, silica nanoparticles, molecular hydrogen, and complex organic molecules. The chemistry of the plume material is consistent with hydrothermal activity on the ocean floor, suggesting that Enceladus has an active system of hot water interacting with rock at the bottom of its ocean. The evidence is so compelling that some scientists consider Enceladus the single most promising place in the solar system to search for extraterrestrial life. Titan does not fit neatly into either of these templates. It does not appear to have a simple global ocean like Europa. It does not vent its interior contents into space like Enceladus. Instead, it may harbour a distributed, heterogeneous network of warm water pockets embedded in a frozen matrix, each pocket a transient microenvironment with its own unique chemical conditions. This makes Titan harder to assess as a potential abode for life, but it also makes it more scientifically interesting in some respects. If life can arise and persist in confined, isolated water pockets within a frozen interior, the implications for habitability across the universe become far broader. Ice-rich bodies with intermittent internal heating are common in the outer solar system and presumably common around other stars. If life does not require a vast, continuous ocean but can instead exploit small temporary pockets of liquid, the number of potentially habitable worlds increases by orders of magnitude. The thermal structure of Titan's interior adds another dimension to this picture. Tidal heating from Saturn is not the only energy source available. Radioactive decay of elements like uranium, thorium, and potassium in Titan's rocky core generates heat continuously, as it does inside Earth and every other rocky body in the solar system. This radiogenic heating is modest but persistent, providing a baseline energy supply that operates independently of orbital mechanics. The combination of tidal and radiogenic heating determines the thermal gradient within the ice shell, which in turn controls where and how much liquid water can exist. Models of Titan's thermal evolution suggest that the ice shell is thick, probably several hundred kilometers from surface to the slushy zone below. This thickness creates a formidable barrier between the surface environment, with its methane weather and organic chemistry, and the subsurface water pockets where conditions might support biology. The two environments are physically close in astronomical terms, separated by distances smaller than the diameter of a modest asteroid, but functionally isolated by kilometers of solid and semi-solid ice. Yet the isolation may not be complete. The 2025 JPL study suggested that rising water pockets could transport material upward through the ice shell, and that organic molecules from the surface could percolate downward through fractures and grain boundaries in the ice. If these transport mechanisms operate over geological timescales, they could create a slow but continuous exchange of material between the surface and the interior. Organic compounds produced by atmospheric photochemistry could eventually reach subsurface water. Water and dissolved minerals from the interior could eventually reach the surface. The ice shell would function not as a perfect seal, but as a slow filter, allowing chemistry to connect two otherwise separate realms. This possibility links Titan's surface chemistry to its interior chemistry in a way that is unique among the worlds we have studied. On Europa and Enceladus, the surface is largely inert, composed of water ice with some radiation-processed compounds. The interesting chemistry happens in the ocean below. On Titan, both the surface and the interior harbour potentially interesting chemistry, and the ice shell between them may serve as a conduit rather than a barrier. The surface contributes organic molecules, the interior contributes liquid water and mineral nutrients. If material cycles between these two domains over millions of years, Titan becomes a world where prebiotic chemistry operates simultaneously in two different media, liquid methane on the surface and liquid water underground, connected by slow but persistent transport through ice. No other known world offers this combination. Earth has liquid water on the surface and geological activity below, but its surface liquids and subsurface processes involve the same solvent. Titan separates the two, placing hydrocarbon chemistry on one side of an ice barrier and aqueous chemistry on the other, with the potential for exchange between them. This dual solvent system is without precedent in planetary science, and its implications for chemistry and potential biology are only beginning to be explored. A molecule synthesized through photochemistry in Titan's atmosphere might rain onto the surface, dissolve in a methane lake, percolate through ice over millions of years, and eventually encounter a pocket of warm liquid water deep in the interior, where it enters an entirely different chemical context. The molecule was born in a hydrocarbon world. It ends its journey in an aqueous one. What reactions occur at that boundary? What products emerge from the meeting of organic chemistry with liquid water under high pressure and moderate warmth? No laboratory on Earth has yet fully explored. The answer matters because it may tell us whether the combination of two different chemical environments, connected by slow transport, can produce molecular complexity that neither environment could generate alone. The 2024 discovery that Titan's surface may contain an insulating crust of methane-rich ice, up to 6 miles thick, adds yet another structural layer to the picture. This methane clathrate crust, identified through thermal modelling, would trap methane gas within the crystalline structure of surface ice, creating a thermally insulating blanket that affects heat flow between the interior and the surface. The insulating effect warms the ice shell slightly from the top down, potentially influencing where liquid can persist and how material moves through the upper layers. The result is an interior that defies simple categorization. Titan is not an ocean world in the traditional sense. It is not a dead ice ball. It is not a straightforward rock and ice body with a predictable layered structure. It is a geologically active, thermally complex moon with at least 3 distinct environments: a methane weather system on the surface, a thick ice shell with embedded slush and warm water pockets in the middle, and a rocky core generating heat at the bottom. Each environment has its own chemistry. Each connects to the others through slow but real transport processes, and each was hidden, layer by layer, beneath the orange atmospheric veil that frustrated astronomers for 3.5 centuries. The December 2025 study did not close the book on Titan's interior. It opened a new chapter. By demonstrating that the Cassini data support a more complex interior than the original global ocean model suggested, the researchers created new questions that only future missions can answer. How many water pockets exist? How large are they? How warm do they actually get? How efficiently do organic molecules from the surface reach them? Do any of these pockets persist long enough for complex chemistry to develop? Could any of them harbour microbial life? These questions will drive the next generation of Titan exploration, and the mission designed to begin answering them is already taking shape in a clean room in Maryland. But before we follow Dragonfly to the launch pad, we need to step back and consider what Titan means in the broadest possible context, because the significance of this world is not just that it has weather, or seas, or warm water pockets buried in ice. The significance is what all of these features, taken together, tell us about the kinds of worlds that can exist in a solar system, and about how profoundly we have underestimated the strangeness, that can hide in plain sight, orbiting a planet visible to the naked eye on any clear night. Stand on the surface of Titan and look up. You would not see Saturn. You would not see the stars. You would not see the sun as anything more than a faintly brighter region in a featureless amber sky. The atmosphere above you would press down with 1.5 times the weight of Earth's air, a thick, cold blanket of nitrogen and methane and photochemical smog extending hundreds of kilometers overhead. The temperature around you would hover near minus 179 degrees Celsius, cold enough to freeze water into a substance harder than most terrestrial rocks, cold enough to turn methane into a flowing liquid that carves valleys into the frozen ground beneath your feet. The light would be dim, roughly 1,000th of a sunny day on Earth, filtered through layers of organic haze that turn everything the color of a deep bruise fading to amber. You would be standing on one of the most alien landscapes ever discovered, a place where the familiar rules of terrestrial geology have been rewritten using different materials under different conditions, producing results that are simultaneously recognizable and profoundly wrong by earthly standards. Rivers that flow with fuel, bedrock made of ice, sand dunes built from molecules manufactured in the sky, seas that would evaporate into flammable gas if you somehow warmed them to room temperature. And this world is not orbiting a star in another galaxy. It is not circling a red dwarf 40 light-years away, accessible only through spectroscopic analysis of atmospheric transit signatures. It is here. It orbits Saturn. You can see Saturn tonight if the sky is clear, a pale yellow dot hanging in the constellation where the ecliptic carries it this season. Titan is right there beside it, invisible to the naked eye but present, hiding behind its orange veil as it has hidden for every moment of recorded human history. This proximity is what makes Titan so conceptually jarring. We have spent decades building space telescopes to characterize the atmospheres of exoplanets orbiting distant stars. We have invested billions of dollars in missions designed to detect biosignatures in the spectra of worlds we will never visit. We have catalogued thousands of exoplanets and speculated endlessly about which ones might harbor oceans, which might have weather, which might support the chemistry necessary for life. And all the while, one of the most chemically complex, meteorologically active, and structurally layered worlds in the known universe has been sitting less than 10 astronomical units from Earth. Not hidden by distance, hidden by haze. The disconnect between Titan's proximity and its strangeness forces a reconsideration of what we think we know about the solar system. For most of the 20th century, planetary science operated under an implicit assumption that the interesting action happened on planets. Moons were secondary objects, geologically dead, compositionally boring, important mainly as gravitational test masses for measuring planetary properties. The Voyager missions began eroding this assumption when they revealed volcanic eruptions on Io and fractured ice terrain on Europa. But even after Voyager, the prevailing instinct was to treat moons as simplified versions of planets, smaller, colder, less complex. Titan obliterates that instinct entirely. Consider the inventory of features that Titan possesses. A dense nitrogen atmosphere with surface pressure exceeding Earth's. A methane-based weather cycle with clouds, rain, rivers and seas. An active photochemistry that produces complex organic molecules continuously. Sand dunes made of atmospheric fallout. Possible cryovolcanism connecting the surface to the interior. A thick ice shell with internal slushy layers. Warm pockets of liquid water enriched by organic molecules and rock-derived minerals. A geologically young surface shaped by ongoing erosion and deposition. Coastlines carved by waves. Seasonal atmospheric changes driven by orbital mechanics. Now compare this inventory to what we know about the terrestrial planets. Venus has a thick atmosphere and surface volcanism, but no liquid on its surface and no weather cycle involving surface liquids. Mars has a thin atmosphere and seasonal frost cycles, but no standing liquid and no ongoing geological activity that shapes terrain at the rate Titan's methane cycle does. Mercury has no atmosphere at all. Titan, a moon, possesses a broader range of active planetary processes than any of the rocky planets in the inner solar system except Earth. It has more in common with Earth, functionally, if not compositionally, than Mars does. This comparison is not an exaggeration for dramatic effect. It is a straightforward assessment of which worlds in the solar system currently operate active cycles of atmospheric chemistry, surface liquid transport, erosion, deposition, and possible interior surface exchange. Earth and Titan. That is the complete list. The atmospheric dynamics alone place Titan in a category shared by no other moon. In May of 2025, researchers at the University of Bristol published a study in the Planetary Science Journal, revealing that Titan's thick atmosphere does not rotate in alignment with its surface. Instead, the atmosphere wobbles like a gyroscope, tilting and shifting orientation with the seasons as Titan moves through its nearly 30-year orbital period around Saturn. The team analysed 13 years of thermal infrared data from Cassini's composite infrared spectrometer and found that the atmospheric tilt follows a pattern driven by the changing angle of solar illumination as Titan seasons. Progress. The winds in Titan's upper atmosphere blow roughly 20 times faster than the surface rotates, a phenomenon called superrotation that also occurs on Venus. This means the atmosphere and the surface are dynamically decoupled, spinning at different rates and wobbling relative to each other in ways that affect circulation patterns, temperature distributions, and the transport of chemical species from pole to pole. This atmospheric behavior has direct practical consequences for the mission currently being assembled to explore Titan's surface. NASA's Dragonfly rotorcraft will enter Titan's atmosphere in 2034 after a 6-year journey from Earth. As the nuclear-powered drone descends through the haze, it will be carried by winds that bear no fixed relationship to the surface below. Understanding how the atmosphere wobbles with the seasons is essential for calculating where the spacecraft will actually touch down. An error in wind modelling could deposit Dragonfly kilometres from its intended landing site. The Bristol study provided atmospheric dynamicists with the data they need to refine descent trajectory predictions, turning a scientific curiosity into an engineering necessity. Dragonfly itself represents an entirely new approach to planetary exploration. It is a car-sized, 8-rotor drone powered by a multi-mission radioisotope thermoelectric generator, the same type of nuclear power source that has sustained Curiosity and Perseverance on Mars. But unlike any Mars rover, Dragonfly will fly. Titan's thick atmosphere and low gravity make powered flight not just possible but remarkably efficient. The atmosphere is 4 times denser than Earth's at sea level, while the surface gravity is only about 1/7 of Earth's. A rotorcraft on Titan requires roughly 40 times less power to hover than the same vehicle would need on Earth. These conditions are so favourable for flight that engineers at Johns Hopkins Applied Physics Laboratory, where Dragonfly is being built, have described Titan as the easiest place in the solar system to fly other than Earth. Construction of the spacecraft officially began on March 10, 2026, following the mission's successful passage through its critical design review in April of 2025. As of now, the integration and testing phase is underway in clean rooms at the Applied Physics Laboratory in Laurel, Maryland. Flight radios have been completed and delivered. The aeroshell that will protect Dragonfly during atmospheric entry has passed fabrication and thermal cycle testing at Lockheed Martin in Denver. The Dragonfly mass spectrometer, the instrument that will analyze surface chemistry for biologically relevant compounds, has cleared its acceptance review at NASA's Goddard Space Flight Center. Rotor performance has been validated in tie-tangent-like conditions during a month-long test campaign in the Transonic Dynamics Tunnel at NASA's Langley Research Center, where engineers immersed a full-scale test model in heavy gas to simulate Titan's dense atmosphere. The mission is scheduled to launch no earlier than July of 2028 aboard a SpaceX Falcon Heavy rocket from Kennedy Space Center. After an approximately 6-year cruise, Dragonfly will arrive at Titan and descend to a landing site in the equatorial dune fields near Selk Crater, an impact structure roughly 80 kilometers in diameter. Selk Crater was chosen because impact events on icy worlds temporarily create conditions where liquid water can interact with surface organic materials. When a large asteroid strikes an ice-rich surface, The energy of the impact melts vast quantities of ice, creating a transient lake of liquid water that persists for thousands of years before refreezing. During that window, organic molecules present on the surface dissolve in the warm water, creating conditions that might drive prebiotic chemical reactions. Selk Crater is old enough that its melt lake froze long ago, but the chemical products of that water-organic interaction should still be preserved in the crater's floor deposits, waiting for an instrument sensitive enough to detect them. Dragonfly will spend over 3 years exploring Titan's surface, making flights of up to roughly 175 kilometers between landing sites. Each flight will carry the rotorcraft across terrain that would take a wheeled rover months or years to traverse. At each stop, Dragonfly will use its suite of instruments to analyze surface composition, measure atmospheric conditions, and characterize the geophysical environment. The mass spectrometer will identify organic molecules in surface samples, with sensitivity far exceeding anything Cassini or Huygens could achieve. A gamma-ray and neutron spectrometer will measure the bulk elemental composition of the surface material. A suite of meteorological sensors will record temperature, pressure, wind speed, and humidity at every landing site. What Dragonfly hopes to determine is how far prebiotic chemistry has progressed on Titan. The mission is not searching for life directly. It is searching for the chemical precursors of life, the complex organic molecules that represent the building blocks from which biology could theoretically emerge. If Dragonfly finds amino acids, nucleobases, or other biologically relevant molecules in Titan's surface material, particularly in locations where liquid water once interacted with organics, it would demonstrate that the chemistry of life is not unique to Earth. It would show that the molecular ingredients of biology form naturally under conditions that exist elsewhere in the solar system, using processes that require nothing more exotic than sunlight, simple gases, and time. This brings us to the deepest question that Titan poses, and it is not a question about chemistry or geology or atmospheric science. It is a question about categories. What kind of world is Titan? The answer seems obvious. Titan is a moon. It orbits Saturn. It is gravitationally bound to a planet rather than directly to the Sun. By every standard definition in planetary science, Titan is a satellite. But definitions are human constructions, and the features Titan possesses strain the usefulness of the category we have placed it in. Titan is larger than Mercury. It has a thicker atmosphere than Earth. It has a more active surface chemistry than any planet in the inner solar system except our own. It has a methane cycle that mirrors Earth's water cycle in structure, if not in composition. It may have warm liquid water in its interior. It has coastlines, dunes, mountains, and river valleys. If Titan orbited the Sun directly at the same distance as Earth, it would be classified as a planet without hesitation. The only reason it carries the label moon is the accident of its gravitational association with Saturn. The label tells us about Titan's orbit. It tells us almost nothing about what Titan actually is. This categorical confusion matters because it shapes how we think about where to search for interesting worlds. The word moon carries connotations of smallness, simplicity, and geological death. When someone hears that a target for astrobiological investigation is a moon, the instinctive reaction is to rank it below planets in importance. But Titan demonstrates that moons can be among the most complex worlds in a planetary system, more active, more chemically diverse, and more scientifically interesting than the planets they orbit. If Titan were located in the habitable zone of a nearby star and detected through transit spectroscopy, astronomers would classify it as one of the most promising candidates for further study in the known universe. The fact that it orbits Saturn rather than a star diminishes its status in our mental hierarchy without diminishing anything about the world itself. The discovery of Titan's full complexity arrived gradually, spread across decades of observation, 3 major spacecraft encounters, and hundreds of scientific papers. This gradual pace obscured the cumulative weight of what was being revealed. Each individual finding, the atmosphere, the lakes, the rivers, the dunes, the possible cryovolcanism, the subsurface water, could be appreciated on its own terms as an interesting fact about an unusual moon. But taken together, They describe something qualitatively different from a mere collection of interesting facts. They describe a world, a functioning, dynamic, chemically active world with multiple interacting systems operating simultaneously across a range of scales from atmospheric photochemistry to deep interior geophysics. The concealment was not just atmospheric, it was conceptual. The haze hid the surface from our telescopes for centuries. But even after Cassini and Huygens revealed what the surface contained, the full implications took years to absorb. Scientists needed time to connect the atmospheric chemistry to the surface geology, to link the surface features to the interior structure, to understand that the methane cycle and the ice shell and the possible water pockets were not separate phenomena, but components of an integrated planetary system. Titan was not hiding one secret beneath its atmosphere. It was hiding a nested hierarchy of secrets, each revealed layer exposing a deeper layer below, and each deeper layer turning out to be more complex and more alien than the one above. The 2025 cluster of discoveries brought this hierarchy into sharp focus. The vesicle study showed that Titan's surface chemistry can produce cell-like structures. The co-crystal study showed that its surface chemistry operates under rules that contradict standard chemical predictions. The subsurface reanalysis showed that its interior is more complex than the clean global ocean model suggested. The atmospheric wobble study showed that even its atmospheric dynamics are more intricate than previously understood. The formation hypothesis proposed that even Titan's origin story may involve violence and complexity rather than simple accretion. Every new finding added another dimension to a world that was already the most multifaceted satellite in the known solar system. What does this mean for the broader search for habitable environments? It means that the range of worlds capable of hosting interesting chemistry and potentially biology is far wider than the traditional habitable zone concept suggests. The habitable zone, the band of orbital distances around a star where liquid water can exist on a planetary surface, has dominated thinking about where to search for life for decades. Titan sits far outside any star's habitable zone. Its surface temperature is nearly 200 degrees below 0 Celsius. Liquid water cannot exist on its surface under any plausible conditions. By the traditional definition, Titan is not habitable and should not be scientifically interesting from an astrobiological perspective. Yet Titan is one of the most astrobiologically interesting worlds we know. Its surface hosts complex organic chemistry and liquid methane. Its interior may harbour warm water pockets enriched by organic molecules and mineral nutrients. Its atmosphere continuously manufactures the molecular precursors of biological compounds. None of these features depend on being in a habitable zone. They depend on having a thick atmosphere, a methane cycle, tidal heating from a massive planet, and a composition that includes both ice and rock. These conditions could be replicated on moons orbiting giant planets in any planetary system, regardless of the host star's luminosity or the system's architecture. Consider how many opportunities for Titangent-like worlds exist in our solar system alone. Jupiter has 4 large moons and dozens of smaller ones. Saturn has over 200 confirmed satellites of various sizes, including Titan. Uranus has 27 known moons. Neptune has 16. That is a single planetary system with hundreds of moons, and only one of them turned out to be a Titan. But our solar system contains only 4 gas giants. The Kepler and TESS exoplanet surveys have revealed that gas giant planets are common throughout the galaxy. Many orbit at distances from their host stars where tidal heating from the planet and radioactive decay and rocky cores could sustain interior warmth on large moons. If even a small fraction of those gas giants host a T-tangent-like satellite, the number of chemically active, atmospherically thick, liquid-bearing moons in the galaxy could run into the billions. This arithmetic transforms the search for habitable environments from a narrow hunt for Earth twins into a far broader survey of planetary systems as a whole. Every gas giant becomes a potential host for worlds where methane weather cycles operate, where organic chemistry rains from the sky, where tidal heating maintains warm interiors beneath frozen surfaces. The habitable zone remains important for finding worlds with liquid water on their surfaces, But Titan proves that surface water is not the only pathway to chemical complexity and potential biology. The moons of giant planets represent an entirely separate category of opportunity, one that multiplies the number of interesting targets by orders of magnitude. If Titangent-like worlds are common around gas giants throughout the galaxy, then the number of potentially habitable environments in the universe is vastly larger than habitable zone calculations suggest. The galaxy contains roughly 100 billion stars. Current estimates suggest that roughly 1 in 5 to 1 in 10 Sun-like stars host at least one gas giant. If even 1% of those gas giants harbour a large moon with a thick atmosphere and active surface chemistry, that amounts to 100 to 200 million Titangent-like worlds in the Milky Way alone. The number is speculative, built on assumptions that may prove wrong in either direction, but the existence of Titan demonstrates that such worlds are not physically impossible. They are not theoretical constructs. At least one exists, and it orbits a planet in our own solar system. This realization connects to a profound shift in how planetary scientists think about the distribution of life in the cosmos. For decades, the search for habitable worlds focused on finding Earth-like planets at Earth-like distances from Sun-like stars. This approach makes intuitive sense because Earth is the only world where we have confirmed the existence of life. But Titan suggests that Earth's configuration is not the only pathway to chemical complexity and potential habitability. A completely different class of world, cold, hydrocarbon-rich, tidally heated, atmospherically thick, could support processes that converge on the same fundamental requirements for life: liquid solvents, energy sources, organic chemistry, and compartmentalization. Whether life actually exists on Titan remains entirely unknown. No instrument has ever detected a biosignature there. No observation has produced evidence that biological processes are operating on the surface or in the interior. The vesicle research showed that protocell-like structures could form, not that they have formed. The bioenergetic modeling showed that fermentation-based life could theoretically be sustained, not that it is being sustained. The warm water pockets inferred from the December 2025 study could be habitable, or they could be sterile. The honest scientific answer to the question of whether Titan harbours life is that we do not know, and we will not know until we send instruments capable of detecting biological activity to the surface, and eventually to the subsurface. Dragonfly will take the first step, but even Dragonfly, sophisticated as it is, will only scratch the surface, literally and figuratively. The rotorcraft will analyse the top few centimetres of surface material at its landing sites. It will not drill through kilometres of ice to reach the warm water pockets below. It will not land on the shores of Kraken Mare to sample the hydrocarbon seas. It will not fly through Titan's upper atmosphere to study the photochemistry in real time. Each of these investigations would require separate, dedicated missions with capabilities beyond what current technology can deliver at Titan's distance from the Sun. The timeline for understanding Titan fully stretches across decades, possibly centuries. Dragonfly will arrive in 2034 and operate for over 3 years. Its findings will shape the next generation of mission concepts, which will take another decade or more to develop, build, launch and deliver to the Saturnian system. A Titan submarine mission, proposed conceptually by NASA researchers, could explore Kraken Mare directly, diving beneath the surface of an alien sea to study its depth, composition and bottom topography. A Titan orbiter equipped with advanced radar and gravity instruments could map the interior structure with precision sufficient to locate individual water pockets. A follow-up lander near the polar seas could sample liquid methane directly and analyze it for dissolved organic compounds. Each of these missions is technically conceivable but programmatically distant. The exploration of Titan will be the work of generations, not individual careers. Consider what that means in human terms. The scientists who proposed the Cassini-Huygens mission in the late 1980s were in the early stages of their careers. By the time Cassini completed its final plunge into Saturn's atmosphere in September of 2017, many of them had retired, some had died. The graduate students who analysed the first radar images of Titan's lakes in 2006 are now senior professors approaching the midpoints of their professional lives. When Dragonfly touches down in 2034, those same researchers will be nearing retirement. The scientists who will design the missions that follow Dragonfly, the submarine, the orbiter, the polar lander, are today's undergraduates and graduate students, young people who have grown up knowing that Titan has seas and weather and chemistry, but who have never lived in a world where a spacecraft was actively exploring its surface. They will inherit the questions that Cassini raised and Dragonfly begins to answer, and they will spend their careers formulating the next set of questions that only a mission launched in the 2040s or 50s can address. This multi-generational relay is the price of exploring a world that hid itself for so long. Because the moon concealed its secrets for centuries, our exploration of it started later and progressed more slowly than our exploration of more accessible targets like Mars. Mars has been visited by dozens of spacecraft since the 1960s. Titan has been visited by one orbiter and one atmospheric probe. The knowledge gap is enormous. We know more about the mineralogy of individual Martian rocks than we know about the bulk composition of Titan's surface. We have mapped Mars at resolutions of centimeters per pixel. Our best maps of Titan resolve features no smaller than roughly 300 meters across. The asymmetry reflects priorities and opportunities, not scientific importance. Titan was harder to reach, harder to see, and harder to justify funding for during decades when Mars dominated planetary exploration budgets. But the case for Titan exploration has never been stronger than it is now. Every major discovery of the past 2 years has reinforced the conclusion that Titan is not a secondary target. It is one of the primary scientific destinations in the solar system, a world whose complexity rivals Earth's and whose chemistry may hold clues to the origin of life that cannot be found anywhere else. The organic molecules raining out of Titan's atmosphere, the protocell-like vesicles that may form in its hydrocarbon lakes, the warm water pockets cycling nutrients through its interior, these are not abstract curiosities. They are components of a natural experiment in prebiotic chemistry that has been running for hundreds of millions of years, possibly billions, in conditions that may approximate aspects of the early Earth before biology emerged. If that experiment has produced anything resembling life, even at the microbial level, even in trace quantities hidden in deep subsurface water pockets, the implications would reshape biology, philosophy, and our understanding of humanity's place in the cosmos. If Titan's chemistry has approached the threshold of life without crossing it, that finding would be almost equally profound. It would define the boundary between chemistry and biology more precisely than any laboratory experiment on Earth has managed. It would tell us exactly how far natural processes can go toward creating life without quite getting there, and it would constrain the conditions that push complex chemistry over the edge into self-replicating, evolving biology. Either outcome justifies the effort. Either outcome makes Titan one of the most important places human civilization has ever chosen to explore. Return now to where we started, a featureless orange sphere hanging in the void near Saturn. For 350 years, that sphere told us nothing. It reflected our telescopes back at themselves, returning only the blank face of impenetrable haze. We assumed, because we could see nothing, that there was nothing worth seeing. We were wrong. Behind the mask was not emptiness. Behind the mask was a world with weather, with flowing liquids, with coastlines shaped by waves, with dunes built from molecules that fall like snow from an atmosphere thicker than our own. Beneath the surface of that world lay frozen terrain, hiding layers of slush and warm water enriched by organic chemistry. And beneath all of it lay the deeper truth that Titan is not just a moon with an unusual atmosphere. It is a concealed alien planet, a world so strange that if we had discovered it orbiting a distant star, we would have called it one of the most remarkable finds in the history of astronomy. But we did not discover it orbiting a distant star. We discovered it orbiting Saturn, a planet that our ancestors watched drift across the night sky for thousands of years before anyone knew it had rings, let alone moons, let alone a moon that would turn out to be one of the most complex objects in the known universe. Titan has been there the entire time. While we mapped Mars, while we photographed Jupiter's storms, while we counted craters on Mercury and measured the hellish pressure of Venus, while we aimed our most powerful telescopes at galaxies billions of light years away, searching for signs of alien worlds with exotic chemistry and unfamiliar weather. One of the most exotic, most unfamiliar, most alien worlds we have ever found was right here, orbiting our own sun, hidden by nothing more than haze. The real shock of Titan is not what it contains. The real shock is where it is. It is the realization that you do not need to cross interstellar distances to find a world that defies every assumption you hold about what a familiar solar system object should look like. You do not need a warp drive or a generation ship or a breakthrough in propulsion physics. You need a spacecraft, a radar, a probe with a parachute, and the patience to let the data tell you what is actually there rather than what you expected to find. Titan teaches us that concealment is not just a property of distance, it is a property of assumption. We assumed moons were simple. Titan is not simple. We assumed the solar system's most alien chemistry would be found on worlds orbiting other stars. Titan's chemistry is as alien as anything we have imagined for exoplanets. We assumed that a world needed to be in a star's habitable zone to matter for astrobiology. Titan matters more than most worlds inside any habitable zone. Every assumption was a veil, and Titan hid behind all of them, behind the atmospheric haze that blocked our cameras, behind the categorical label of moon that lowered our expectations, behind the vast distance from the habitable zone that made it seem irrelevant to the search for life, behind the apparent familiarity of the Saturnian system that made it seem like explored territory rather than uncharted frontier. Beneath all of those veils is a world we are only beginning to understand. A world where methane rain splashes into hydrocarbon lakes and may stir up the molecular precursors of primitive cells. A world where warm water hides in pockets buried beneath kilometers of ice, cycling nutrients from a rocky core through a frozen labyrinth. A world where the atmosphere wobbles like a gyroscope and the chemistry defies the rules of the textbook. A world that may have been born in a cataclysmic collision between two ancient moons, forged in violence and disguised in fog. Titan is not hiding one secret beneath its atmosphere. It is hiding an entire category of possibility that we never imagined could exist so close to home, and we have only just begun to lift the mask.